Hello, today we're going to be proving that log n is big O of n. That big O of n upper bounds log n. That is less than or equal to big O of n. To do this, to prove this, we're going to work off the following assumption, the following claim. This is what's going to help us. This is going to be our base case in terms. So for n that is greater than or equal to 1, that log n is less than or equal to n. This is going to be basically our base case, and we want to show this. We want to show this behavior all the way through to show that n is upper bounding. So to get an idea of this, let's set n is equal to 1. Let's work through an example. Let's say log, let's choose a base 2. Computers usually work in base 2, so we're going to work with base 2. 1. So this is going to be our first example to show this up here. So n equals 1 at this point, base 2, and the log. We want to show that is still less than or equal to n. To work through this, let's work through this. So this is saying that what 2 to the what gives us 1. 2 to the what gives us 1. We know that 0, 2 to the 0 gives us 1, so this is going to be equal to 0. Now, let's see if it holds. 0 is less than or equal to 1. So it holds. And now let's choose another nice number. Let's choose a nice number. Let's choose 4. Let's choose 4. Now, 2 to the what gives us 4? 2. 2 is less than or equal to 4. So this holds. So this is basically the assumption that we're going to be going over, that we're going to be using. So now we're going to say, this is what we're going to work off for induction. We're going to say that n is equal to k. We're going to use k here for our induction. Now, we're going to assume that this holds for k is greater than or equal to 1. K is greater than or equal to 1. We're going to assume this works. Now, we want to show that k plus 1 also holds. We want to show that k plus 1 also holds. So to start this, let's choose, this is an inequality problem. So this is an inequality problem. We have log k plus 1. Now, we want to choose an inequality that's going to help us out here, something that's going to be easier to evaluate than just k plus 1. We can conveniently choose, we can just choose something. For now, let's choose 2k. This is going to help us. We're going to choose 2k since we know that log 2k is greater than k plus 1. Okay, so we're gonna go off this fact. It's going to help us. Now let's evaluate log 2k instead. We know that this is equal to by the product rule. Remember, the product rule is log ab is equal to log a plus log b. Now, that means log k plus log 2. Now remember we said base was 2. Now this is going to easily work out so we can cancel here. So we can say 1 on the bottom. We can say 1. So log k is equal to log 2 to the k. Now we can start substituting back in. We said previously that log k plus 1, we said this fact up here. We're going to use this fact down here, and we're going to substitute 2 to the k. We're going to substitute 2 to the k. We're going to say log k plus 1 is less than or equal to log from here. We're going to substitute in from this. Log k plus 1. Now, by our inductive reasoning, it seems that k plus 1 still holds. By our inductive hypothesis, we can then say that for sure that log n is less than or equal to n to show that this holds. Now, if this is true, that must mean that log n is big O of n. There's a different color. Again, that log n is big O of n. And this is the proof. Thank you for watching. If you enjoyed this video, remember to like and subscribe. If you want to view more of this content, in the description there's a repository that is an open source textbook, meaning anybody can contribute. More examples, more topics on algorithms. Thank you for watching.